Welcome to the ideal gas video. By the end of this video, you should understand what an ideal gas is and the assumptions we make as part of this model. You should be able to perform calculations using the ideal gas equation. And you should be able to perform stoichiometric calculations using molar volume and the ideal gas equation. Ideal gases are theoretical gases that are described perfectly by kinetic molecular theory. In other words, they're gases that we make up. They don't actually exist, but mathematically we can model them really precisely. And it turns out that most gases under normal conditions, meaning normal atmospheric and temperature conditions at which we work, actually behave a lot like ideal gases. So this model works incredibly well for most gases under the conditions we'll be working. In a future video, we'll explore ways in which real gases can deviate from ideal gases, but for the most part, they don't. So ideal gases don't exist because in order to model an ideal gas, we make two knowingly false assumptions about them. The first assumption is that gas molecules take up no space. In other words, the space between gas molecules, represented by these little red dots here, the space between them is so much greater than the volume of the actual particle itself that we can kind of assume that the volume of the actual particles is negligible. So when we talk about gas volume, most of that volume is just the space between the particles. This diagram here is showing if we took all of the gas particles in this container and sort of solidified them, condensed them down into a solid, they take up just a tiny, tiny fraction of this entire container. So we can kind of ignore the volume of those particles themselves. We also assume that gas molecules do not attract each other. In other words, there's no forces between molecules. This is mostly true because gas molecules are incredibly far apart. And recall, based on Coulomb's law, the farther apart two particles get, the weaker the forces between them will be. And since gas molecules are so far apart, we can essentially say that there are no forces between them. Again, both of these assumptions are false, but they're close enough to true that the ideal gas law still works. So what is the ideal gas law? The ideal gas law describes the behavior of an ideal gas in terms of pressure, volume, temperature, and number of moles of gas. This is a combination of the gas laws that you learned actually last year for most of you in first year chemistry. If you recall, in first year chemistry, you learned that pressure and amount of gas are directly proportional. You might remember P1 over N1 equals P2 over N2. In other words, if you double the amount of gas, you'll double the pressure. Likewise, you learned that pressure and volume are inversely proportional. If you double the volume, you'll half the pressure. And pressure and temperature are directly proportional. If you double the temperature, you'll double the pressure. It's important to note that this is only true for Kelvin temperature, though. Recall that Celsius temperature is not directly proportional to pressure, so you must be in Kelvin when dealing with gases. So the ideal gas law is mathematically expressed as PV equals nRT, P being pressure, V being volume, N being moles of gas, T being temperature, all those things we talked about in first year chemistry, and then R is called the universal gas constant. It's actually a combination of the constants from all three of the equations that we looked at before. But the value of that is on your reference table, and it's shown here, 0.08206. Note this complex unit. This will help you remember what units you need to be in for each of these factors here. Pressure has to be in volume has to be in liters, pressure in ATM, temperature in Kelvin, and amount in moles. And just to remind you, I'll make that spin. Just some reminders about conversions. Remember that pressure can be expressed in many different units, but the ones you'll most commonly see are torr, millimeters of mercury, and ATM. We'll be working in atmospheres or ATMs, so here's the conversions. Kelvin is the Celsius temperature plus 273, and of course there's 1,000 milliliters in a liter. So these are some useful conversions to get everything into the right units to be able to use the ideal gas law. From there, it's mostly just plugging values into the equation. So here's some to try. Pause the video here and try these on your own. When you come back, I'll reveal the answer. Make sure to pay attention to your units because most of these are not expressed in the units they need to be in. Welcome back. Here's what you should have gotten. Notice I converted all my units to ATM, liters, moles, and Kelvin where needed. Since we're assuming that all gases behave like ideal gases, we can actually basically ignore the type of gas we're dealing with when doing gas calculations. Since, remember, we're ignoring the volume of the particles and any potential attractive forces, then the particles are just dots in space, and it doesn't actually matter how those dots behave. As long as they're in the gas phase, the gas will behave like an ideal gas. So the effect of this is if we have samples of gas, regardless of what gas it is, so here we have 3 different samples of gas, under the same conditions of volume, pressure, and temperature, we'll have the same number of gas molecules. Notice the mass of the gas will not be the same because helium, nitrogen, and methane each have different masses, but the number of moles will be the same as long as all these other factors, volume, pressure, and temperature, are the same. This allows us to perform these calculations using PVNRT, or PV equals nRT, for any gas, regardless of its identity. Now let's think about molar volume. According to the assumptions of kinetic molecular theory and the ideal gas law, 1 mole of any gas will occupy the same volume, and that volume will be 22.4 liters as long as you're at STP, or standard temperature and pressure. In chemistry, we define standard temperature and pressure as 273 Kelvin and 1 atm. In other words, regardless of the identity of the gas, if you have 1 mole of it at 273 Kelvin and 1 atm, it will occupy 22.4 liters. This fact allows us to do some stoichiometric calculations as well. Here's a couple of questions related to molar volume. Pause the video here and see if you can answer these on your own. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice in each case I can do basic stoichiometry using mole conversions, and then knowing that 1 mole equals 22.4 liters, I can convert between moles and liters. Again, this is assuming we're at STP, which we are in the first 2 problems. In the third, you had to be a little more creative because I did not give it to you at STP. Therefore, you had to actually use PV equals nRT to solve this. That brings us to the end of this video. Let's review our goals. First, we looked at what an ideal gas is and the assumptions we make in the ideal gas model. Then we learned how to perform calculations using the ideal gas equation, or PV equals nRT. And then we learned to perform stoichiometric calculations using molar volume, 22.4 at STP.